scratch.
Hello. Let's start with sets. What is a set? In mathematics, a set is a collection of distinct objects, usually with a common feature. For instance, a set of animals, a set of planets, a set of polygons, or a set of numbers. Each object inside a set is called a member or an element of that set. Although it is usual to build a set with elements with a common property, it doesn't have to be that way. A set with a boat, a galaxy, and a ghost is still a set. The nature of a set relates to the nature of the elements themselves. It's not about how they are represented. A set with the elements 1, 2, and 3 is a set of words if the elements are supposed to be words, or a set of numbers if they're supposed to be numbers. So far, this is not a linear question. It depends on the context in which we are building the set. To describe a set in a more mathematical way, we don't have to make all those drawings. Those diagrams we used before, to describe those sets, are called Euler-Venn diagrams. To refer a set, we usually use a capital letter, A, B, C, D. And then, describe the set writing the elements, within a pair of curly brackets. A, the set with the platypus. B, the set with Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. C, the set with a triangle, a square, a pentagon, and an hexagon, and D, the set with the numbers 1, 2, 3, 4, 5, 6, 7, 8, and 9. Those sets are called extensional sets, because we describe them by a list of their elements. If we can define the elements by a rule, we may describe A as the set of laying eggs non-echidna mammals, B as the set of all the planets of the solar system, C as the set of the polygons with no more than 6 sides, and D as the set of the positive numbers with just one digit. Those are called intentional sets. There is, however, another way to describe a set, using curly brackets. If we can spot a regularity on the elements of a set, we may write B as the set with Mercury, Venus, Earth, through Neptune, C as the set with a triangle, a square, until an hexagon, and D as the set with the numbers 1, 2, 3, 4, through 9. Those are called ostensive sets. The set A only has the platypus, so there's no regularity to spot on. An ostensive set is kind of like an extensional set, so, in this channel, we will not distinguish them. Do you want to check what you learned? Grab a notepad and write the answers to the following questions. The number of elements of a set is the cardinality of that set. Let P be the following set: orange, pear, plum, banana, apple, and peach. Now, let's count the elements of P. P has 1, 2, 3, 4, 5, and 6 elements. Then, we can write, cardinal of the set, orange, pear, plum, banana, apple, peach, equals 6, or cardinal of P, equals 6. We may also write like this. Or even, like this. Why do we, mathematicians, write the same things in so many different ways? Usually, we hear that mathematics is the language of the universe, and is the same everywhere, and every when. Well, that is true. At least, we think that is the truth. But the syntax? That is not that universal. It depends on the author, and on a trend line. But that's okay. We just have to clarify the readers, and tell them what kind of syntax we are using. And then, we can write the symbols we find more useful, or appealing. A set with just one element, that is, with cardinality equals to 1, is called a singleton. The set A is a singleton. Otherwise, is called a non-singleton. B, C, and D are non-singletons. If a set has no elements whatsoever, is called empty set or null set. A pair of curly brackets with nothing inside is the empty set. The cardinality of the empty set is 0. We use the symbol null sign to represent the empty set. Technically, the empty set is also a non-singleton because, by definition, its cardinality is not 1. Imagine we put all the possible singletons on the left side of the screen. And now, imagine we put all the possible non-singletons on the right side of the screen. Now, on which side of the screen should we put the empty set? Exactly. On the right side. That's it. The empty set is also a non-singleton. A set can also be a finite set or an infinite set according to its cardinality. Let F be the set of the positive even numbers smaller than 20. Let's write F extensionally. F equals 2, 4, 6, 8, 10, 12, 14, 16 and 18. F has 9 elements. F has a finite cardinality. So F is a finite set. Now, imagine the set G of all the positive even numbers. Let's try to write G extensionally. G equals to 2, 4, 6, 8, 10, 12, 14, 16, 18 and so on. Obviously, we can't write all the elements of G on a complete list. But we can write G extensionally, like this. However, we can't count all the elements of G, and, therefore, G has an infinite cardinality. So, G is an infinite set. Let's now mix up the definitions we talked about so far. A finite set may be a singleton or a non-singleton. The set A with the platypus has cardinality equals to 1 and, therefore, is a finite set and also a singleton. The set B of the planets of the solar system has cardinality equals to 8, so is also a finite set. However, B is a non-singleton. But an infinite set is always a non-singleton. The set G of the positive even integers has infinite cardinality. So G is an infinite set and is also a non-singleton. This seems a little confusing, but the truth is, in mathematics, the definitions aren't, in general, mutually exclusive. A square is also a rectangle. An integer is also a rational. An equation is also a condition. And an infinite set is also a non-singleton. To master this way of thinking, you have to practice, and simply watching YouTube videos will not be enough. So, grab your notepad and write the answers to the next questions. Feel free to pause the video, or to rewatch the segments you need. Thanks for watching. And, until our next video, keep scratching the math.